when they say, hey, what's the force of gravity? And they just say 9.8. Oops, what'd you forget?
Negative.
Okay, what else you forget? Mass times, oh, that's good too. Mass times 9.8 meters per second. Oh, mass, well, yes, okay. So the G is 9.8 meters per second squared. Good. And if you multiply it by a mass, then you've got that. And then the force of gravity is always there. Hey, what about at the peak when you throw something up in the air, like a can of cold yoo-hoo? So at the peak, what is the force of gravity? It's the same. Come on, yeah, exactly. Okay. So here's some nice little normal force. Great notes. And even the classic banked curve problem, there's a great example with that. Has springs in there, and let's see if smartboard's, yay, smartboard's working. Although, wow, okay, I can get over it. And it's tiny. I wish okay, yeah, it's a projector setting. Oh, where's that little? What about if we said auto again? Fill rhythm. Okay, auto is. All right. Frame one. Check. Go with it. Some really great examples. Do stuff like after you draw a free body diagram, then you can see what your sum of the forces are. Some of the forces in the x, some of the forces in the y. Let's get down to the fun problems, which happens. Hey, wouldn't it be neat if these were page numbered? And I bet they're not. Also on my page number 20-ish, then they even have, hey, AP Physics C, acceleration. Give me calculus explanation for acceleration. I like that. So how about just the first derivative of velocity also is great. So there'll be times that they say, hey, write a differential equation for velocity, and you're like, well, I knew Newton's second law, F equals ma, and acceleration is the dv/dt, and that these are called differentials, and so that's called a differential equation because it's got an equal sign in it. So cruising down to the problem with integrals. How far are you all in calculus at the same time?
Yes.
And have you recently just got to integrals, or you're not there yet? They'll show up sometime. And so that's the fun thing about Physics C is we try and hold off some of the integrals until you guys get to in calculus, but sometimes they show up and we try to explain things as we're going along. So I teach both the AP Physics C and the calculus, which is great because I know the students in both. Aha! We got to it. And so we have a couple of questions, free response questions. Free response question number 1 and 2 in there. I believe this one must be the answer. So yeah, let's not. There it is.
So you're going through the pages, but it doesn't show the bottom half. So if you scroll up, that's where the problems are. Like
6 from the back is where you have a free response. Yeah. So yes, if you start at the back, then start back there's like so we're going to have some fun with some of these multiple choice questions here in just a little bit and explaining those. But I want to get something else before we get to the multiple choice. And so, oh, these are nice. And so take a few minutes and you can work with your friends and try to, as quickly as you can, put some stuff down for the free response. Now, the free response question number 2, where you draw on 3 free body diagrams for the moment the coffee filter was released. Hey guys, have you ever seen a coffee filter?
it's like very.
Yeah, we didn't do that yet.
I understand. In fact, yep. Wow, it's on. Sure. So this is like a coffee filter, except it's actually Kleenex. And so the moment you release it, and then the next one was before it reaches terminal velocity. Terminal, you've heard of like terminal cancer or something like that. It's the end, and so it's the maximum velocity. It's increased speed more and more and more until it's reached that maximum speed. So draw 3 free body diagrams. Oh, look at that. Question C, write a differential equation that could be used to solve for the speed. So from your free body diagram, see if you can do some of those really split. And I'll get one more thing queued up for these enjoyable multiple choice questions. Yes. So
like, is this supposed to say which block we're supposed to go?
Yeah, it does.
Because it just says on block.
On block.
it's, yes, actually, yes. Good observation. Do that. Let's go with block 2.
Okay.
Yeah,
I was just like,
block 2. Because
not sure what's happening.
yeah. They want to give you 2 dots if you want to do it for one block.
On block.
One block.
Yes. I did notice that too. Thank you for saying something.
The second block is.
This part, the center part is friction loop.
It says it's
But
friction
this
loop.
part,
Well, that's what's keeping it from sliding.
Yep.
Which is
yeah.
part B.
Nice. I wonder why that HDMI cable wasn't working for you.
They have a Wi-Fi.
For gravity, I've got to get more cool stuff for the gravity.
Part what?
No, it has Wi-Fi.
For B, you have to see the force of friction.
You can't use anything with
Static, and you have to, like, so basically we have to know that the force of gravity and the direction that would make it move can never be greater than like,
Oh, you can take it out.
Like the
So
force
you
of
guys-
gravity can never be greater than the force
You guys
of
know that when you
gravity.
have a free body diagram of something at an angle, then oftentimes, pretty much always, except for on the banked curve problem, when you have a car going around a banked curve, then you turn your little axes. You have the x-axis and the y-axis all at an angle. Got 2 more. Here's my 2 more. I'll go more. There's one. And sweet. Perfect. Okay. So, let's take a look at the solutions for the first part here. And go. Unfreeze. And unfreezing. So, of course we have, we get 3 points, 1, 2, 3. 1 point was deducted if you had anything else, or if you broke things up into their components. So the next one, determine the maximum angle 6 points for this guy. And what you want to do is, the incline can be made without the block sliding down. This tension, from the other free body diagram, you know that tension, here's the one that you didn't have to draw. Might need to try aligning with the weirdness. Click. Well, that's loud. Shh.
Yeah.
You don't need to go. We'll do that 9 times. Close enough. And victory. So from the other free body diagram, you have the tension is equal to that force of friction. Yep, sure do. And you wanted, and you know what the static frictional force is. That would be the maximum. And so this tension going this way, which is equal to that force of friction, from the sum of the forces of the other one, sum of the forces for the red one, yours isn't red, in the x direction is equal to, is this thing accelerating? Not for part B, not for that part of the question, is it?
0.
The maximum angle so that it just starts to move, right?
Doesn't move.
Oh, it does, yeah, exactly, so it doesn't move, so it's not accelerating. But some of the forces is always equal to ma, but a whole lot of times that a is 0, right? And so yes, that force, that tension, this tension is equal to that force of friction, the mu times our normal force, and the normal force being mass of number 1, divided by high screen videoing. And so what do we need to do? And don't do this on your free body diagram, but you need to break it up into its components. You need to go da 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 da. Really? Oh, there was that thing. Dot 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 and dot 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 dot. So you got this. You guys know about this is your angle right here.
Theta's
Yes,
right there, yeah.
theta is this one. In other words, it makes a right triangle. So we won't try to explain that again. But the essence is that force of tension, aka that force of friction, that mu times the mass of number 1 times gravity. Did they label in the given? I have to scroll up. Oh, I can almost see it on the tiny one.
Want me to get to that?
Sure. Yeah. So we can see the rest of the question.
It gave us the static friction is 0.6.
Yes. Good. Well, that's almost. Is equal to the what's this component going down? Which trig function?
Maybe cosine.
How about the
you the x one, that's
this
sine.
x, yeah, the opposite side. This x, the one that's going in the same direction as the
Yeah,
tension.
so
So yes,
sine.
G, yeah. How about actually m for number 2? Are they the same mass?
Same mass.
They're the same mass. Well, that's nice. Mg sine of theta. So there you go. Hey, look, they both have the same mass. And they both have the same acceleration of gravity. Yeah. So that's what you were looking to do from your free body diagram stuff. Freeze. And then, can't scroll on that one.
Yeah.
No, I mean, like, is it a smart
No,
board?
yeah.
Are you trying? So are we trying to get the theta alone? So we have to divide by the inverse or not?
I wouldn't call it divide, but yes, take the inverse sine of both sides. Yes, do the inverse sine of both sides to get it by itself, and that would be that maximum angle would be theta is equal to the inverse sine of the mu. Isn't that interesting? So we were doing the force going down the incline, that component of gravity, the force of gravity in the x direction, force of gravity x direction. We were saying that that's equal to tension. But from the sum of the forces in this x direction on the incline, see how it's on the incline, would say, hey, let's go x that way, and y is this way. You can almost see that on this. Then on the next part, we're going to say that's equal to ma. Yeah, you find some sort of interesting little. There's something else funny about this question. There was a deficiency, I believe, in it. So if we gave it a little push and got it started, then part C, then assume a 30 degrees, find that angle, and yeah, finish off your part B, and then good. So this is some nice things for part C. You're just using this, but this time it is MA, and you're trying to solve for that MA, and you can set the two forces acting on, of course, are tension and this component of gravity, or you could say mg sine theta, the component of gravity going down the incline, minus the force of tension. Yeah, which will be equal to,
Force friction.
well, yeah, definitely will still be equal to the force of friction. Because that tension is that way, and no matter what, it's good. Just getting it. That's nice. So then you can see the other parts of things. So, but I do want you to get to the next part where you actually get to do that, write that differential equation that we alluded to. I'm curious if you could write that. So how are the 6 points divvied up? For doing some sort of, the sum of the forces is equal to 0, and for block 2 you have tension minus
FP?
Yep, that's guess that's going to be the parallel to the slope.
Yeah.
I was like, I would call that x. Yes, the mg sine theta, and points, and like we got the inverse sine of 0.6. And if you were in degrees, then you would get 37 degrees. And then this one was a little funny in that you have to assume it's moving. What kind of friction do you have if it's moving?
Kinetic.
Then did they give you the value for that?
Yes.
Yes, sir.
Yes. And so with that value for it, then you do the same type of stuff that we were doing before. Tension minus the kinetic friction is equal to MA, and yada yada yada. So, yep, it gets a little bigger and good times. But so go ahead and move on to number 2, because I want to see if you guys can write that differential equation, draw those free body diagrams for that. Yeah.
Oh, he's doing that.
Yeah, I'm doing that.
I thought I just messed it up.
I downloaded the virus or something. It was like, I swear I did not break the gravity limit. Just let me
Check. Sweet.
Is this even a calculator?
Yes, sure. Does do graphing and calculating, but yes, you are correct.
Tab out.
Okay.
Probably no.
Yep.
What's the name of
So,
I don't know what that is.
I'm gonna take a look around at your free bodies. Oops, so you need to do, yeah, 2 more. You got the, ooh, when it's first dropped, what is the air resistance? You know the air resistance depends upon the velocity. And when it's first dropped, the first one, you're not gonna have any force going up. You're not gonna have any air resistance force going up. On the next one, it's gonna get a little bigger, and on the last one, it's gonna be equal to it. Yep, and that's what you wanna show. In the part B, so yeah, if you did that, which I guess I go ahead and show that picture, unfreeze the screen, coffee filters, yes, unfreeze. There you go. Yep, only weight, and a small force, drag force going up, and then a drag force that's equal to the weight on the third one. In the second part, which is nice and big, but
I'm sorry.
I'm sorry. If you could do the, yes, perfect. Use new second law to determine the terminal speed of the coffee filter. Terminal speed. Which one of your free body diagrams are going to be using to find the terminal speed?
The after terminal.
The one, yeah, that one. Right, good choice. And so, do the sum of the forces. You're doing your sum of the forces in the y direction. What's it always end up to be equal to? Well, it always has to be MA, but you're correct. It is 0 in this particular problem. Absolutely. And what are the 2 forces on it?
Force of drag force
Or drag or air resistance. And
force of gravity.
we want to call it mg this time, or yeah, force of gravity. And determine the terminal speed. I think we probably know certain letters, like now. Oh, neither of them are up there far enough. Yep. Lowercase m for the mass. Oh, look, they gave us an interesting equation for the drag force. So use that. What's that minus sign doing there?
It's the opposite direction of the force.
Beautiful. Yep. Exactly. So, for example, Hooke's law, that negative kx. The negative is just there to tell you it's a restoring force. It'll tell you about the direction. And so, when you're putting it into your equation, and you're like, I'm not going to use the negative. I'm just going to write whatever that, a kmv squared equals mg. I think we're trying to solve for b. Can you do that real negative split?
What was that law you said?
Hooke's
There's
law?
a guy called Hooke's law about springs. The F is equal to a negative kx. So yeah. And so similarly, that negative was just there saying that there is a restoring force that is proportional to how far a spring gets stretched. And I look around in the physics room for where the spring is hanging from the ceiling. Oh look, there's some springs hanging from the ceiling. So as in spring scales, spring scales.
So the negative, like in front of the K, like you're just showing us opposite gravity, but like so you don't really need that.
Right, not for the equation, right? For one thing, it'd be a little awkward. Hey, square root of a negative number.
Yeah,
I got imaginary velocity. Solving for V. And almost a winner. Boom, got it. And found it.
And then you got it. Thank you.
And now do the part C. So similar to what we did here, but it's not, the acceleration is not going to be 0, is it?
That is actually our next lesson.
About the writing it.
So,
Sometimes these mornings are review and sometimes they're preview.
yeah, I
And-
don't know exactly what a differentialization is.
We
I don't know if y'all
rules
did
of
that in-
differentiability.
Nice.
Would you
Did
start
that
with
in
the
calculus?
Yeah, but we haven't gotten to like
Like
this
this?
virtualization.
Well,
I mean, right?
so you have it here, and we talked about it earlier. So acceleration, what's the definition of acceleration in terms, calculus terms?
Derivative velocity.
Derivative velocity. So if you write that, you get full credit.
Okay, so we just
Yeah.
put the derivative.
Just substitute the A, and it's a very popular thing to do on those AP exams. When they say write differential equation, you're probably like, I wonder if you just want that acceleration is the dv/dt. Later on, when you get to rotational motion, it might be something else, but let's not mention that right now. And so yeah, you just write your stuff that you had before. Which way is it accelerating? when it is accelerating?
Down.
Down. So this one I was a little, I did the up one first, which is fairly common to do up first. But since I want maybe down to be positive, then maybe I'll switch the order. I mean, I guess I could have just said, hey, down is negative, and so I could have put a minus MA over here, and it would all work out real nice. But anyway, I think for my part C, we're writing a different, it's the same stuff as we did right there, but this time that's all you got to do is put in what A is, and you're saying it's a dV dt. Hey, look at those cute little differentials. The infinitesimal small little amount of time. Oh, there's an M right there. And hey, look, now it's a differential equation because it has an equal sign. And I just have to write the other stuff. I think I'm going to go ahead with the mg, and how about, ooh, and it's real satisfying because look, it's a minus. kmv squared. Well, there you go. We have written a differential equation that could be used to solve for the speed of the coffee filter as a function of time, but we're not going to solve for v, because for one thing, that one's a hard one to solve for v. It's not even a pretty one that we usually do, where it's like natural log.
So why did you switch up the MG and the
No, it was about which way is positive. I said, hey, let's say that down is positive this time, and so if down's positive, then that's going up. Yeah. When it's equal to 0, it doesn't necessarily matter which one, and yeah, it wouldn't matter. So, mission accomplished on, turn it over, and can you draw correct reasonable graphs? So take a second and draw that, and then we'll be moving on to some very response good times. Nice. Because of the concavity, this is concave up and then it's concave down, and so you just want to do the same kind of concavity. So now it's be starting at 0.
Accelerating, because as the force gets closer to it, it's
That means yeah. Yes. How about this? Immediately, what kind of acceleration? Because what's the slope of the velocity time graph? What's the slope of the velocity time graph? Yes. And so this slope is the acceleration graph, and then it's full speed of that bubble starts at 0. Beautiful. Nice. Nice. Yes. Hey, everybody else, what's the slope of a velocity time graph? Acceleration. And so for your graphs that you have been doing, it starts off with what kind of acceleration? About 10 or 9.8 meters per second squared going down, and then it's going to reach that. A better. Dot. Yeah, I don't want to go above that terminal velocity. I want to be reaching that terminal velocity. That's better. So, yep.
This is a curve in it?
It's, shall we say,
The acceleration is decreasing.
yeah,
as
shall we say
time
it's
goes on.
asymptotically approaching that terminal velocity? Although in physics world it actually gets to it and it stays at it. But you know, mathematically we'd be like, hey, look, it's getting closer and closer. It does reach a terminal velocity. And if you do that coffee filter lab and you have a little motion detector underneath it, which we recently did, and I could show you the data for it because it's so cool. But let's go ahead and see the answers. Using Newton's second law, we said, or you guys said, that velocity, the terminal velocity, is that square root of a GH. Lots of points for you for that. And then, hey, look at that. dV dt is equal to the G minus KV squared. Yeah, they took out the masses. You actually, you would not lose a point for having masses in there. Because it is a differential equation. It just still have masses in it. So it'd still be beautiful. And ready, here's how the points were awarded for your curve. There's your curve. AC, they actually reached it. 1 point for, they called it a square root curve. I don't know. Well, I could see it because look, it says square root, right? Sure. Actually, so that's what the maximum speed is. They actually labeled it, which is kind of nice. 1 point for approaching a maximum speed, or a curve that is concave down as the velocity increases. 1 point for the curve approaching asymptotically the terminal velocity. So anyway, we wanted to do the nice little curve that a lot of you guys drew. And then what's up next is acceleration. What kind of acceleration to start out with? Started out with that gravity. And so on the axes below, and they did have both sides, so you could start out with a negative 9.8. What they did was they just did yours would not be wrong if you said negative, unless there was some point where they said
It says to make down
oops,
positive.
oops, except it said to make down positive. So except it said that. So that is one of my biggest tips for taking an AP exam, whether it's your AP Calculus or your AP Physics. After you answer the question, read the question real quick one more time. Make sure you actually answer the question they were asking, and not just the question that you were thinking that they were asking. Yes. And so if we, that last sentence usually gives you a nice little hint. Like, don't forget units. You're like, oh, thank you. I'm glad I read that again because I need to include units. This one says take down is positive. And so therefore we're going to start out with a nice positive velocity. So that's why it started out at a positive g and it decreased until the acceleration was? Zero. Yep. All right, good stuff. Now, I'm excited to ask you a question that I think you're gonna get super fast. This one's called, they're called little quick polls when they come up on your screen. It's number 10. And so if you flip to the multiple choice, here is number 10. And let's see if everybody's getting a nice little question popping on their screen and can find number 10. Yep.
How do you select it?
On the bottom of E.
Scroll.
Yeah, just scroll through. Like she said.
How do I enter it?
You click the middle button.
That's it?
Sure.
You don't have to like enter it or you just select it or do you
Yep. No, as soon as you select it, I've got. So great job for, let's see, how many people? We got 9 out of the 15 of you have made a choice. And I have a feeling that all 9 of you, I don't know, is it okay, we're up to 10? Does everybody say the same thing? Almost. So D does look really good, right? So yes, D is the correct answer for that one. Hey, it's not too late to change your answer. Yeah, beautiful answer for that. Now that you know that, okay, I tried to warn you. It's a little tricky. It says, what is the force of static friction acting on? This is number 11. I'm pretty confident that we're not going to get as high of beautiful results because they're going to fool you, and then I'll get to explain why they fooled you. But go ahead and pick something, and so I'll know when most people have made a choice
How
because
expensive are these calculators?
about the same as the 84s.
Oh.
Yeah.
Well,
Yeah.
I don't get that.
Yeah.
It moves like a nut.
Yeah, especially these 84s. Definitely the same price as these cool 84s.
That would be so I would be so stressed out about that.
What is that, 8 people? Yep, 9 people made their choice. With the AP Physics C, you can give yourself a little bit over a minute for each of those 35 multiple choice questions that you get 45 minutes to do them in. And so so we've had about a minute. So another recommendation is go ahead and make a choice. Even if you're like, I don't know, because you're not penalized for guessing. And so it'd be fun if we had 100% of the people replying. There you go, 12, let's go.
3 more people.
Yeah. And here's what people are thinking. Oh, look at that. People are thinking everything. And oh, there you go. Way to fill it in. So now everybody's, okay. Nobody gets left out. So C is really popular. However, like I was saying, I think that's going to be the tricky one. Why is that? Why is C the tricky one? So you, from your nice little free body diagram, which D looks great, right? And so you break it up into its components. You're like, hey, this force going down, this mg sine theta going down the incline is going to be equal to my mu times the normal force. And so you're like, okay, it's equal to my mu times the mg cosine theta. But the problem, let's get, oh, it says what is the static frictional force? Okay, so there it is. So you're thinking, that's better. You're thinking that it says what is friction. It's good to know what it is you're asking. So what is the frictional force? And you're thinking it's mu times the mg perpendicular cosine theta. That's what you're thinking. Very popular answer. However, static. This is not an equal to. It's a less than or equal to. It's a less than or equal to. So on an incline, which usually we, let's see. Sometimes these have nice little friction. Yeah. Okay. I wish I were getting time. Oh, good. Figure inclines. Okay. So, mu times the normal force. Okay. That one doesn't have little things on. Does yours have a normal? No, yours has it on it. Some people take the little friction things off. They're like, oh, I need friction sometimes. Yes, beautiful. So there's this friction. Now, mu, the mu times that normal force, that's the maximum it is. So it's kind of like this. If it was on a flat surface, and you're like, okay, I found out that the mu times the normal force is 10 newtons, and I'm going to push this thing with 1 newton. So 1 newton this way, and you're like, yeah, friction is 10 newtons this way. Do you see what's funny about that? So if I'm pushing 1 this way and friction is 10 that way, then it'd be going that way. Yeah, you start to push something that goes that way. That's what's up with that less than or equal to. And so the correct answer is up there. At least a couple people maybe have chosen the correct answer. Friction we're not going to have a mu in our answer. From this free body diagram, the friction is equal to this component of gravity. It doesn't need to be any bigger than whatever this component of gravity is. There we go. Yeah, it's equal to that mg sine theta. Yes, we're almost at 100%. And if this was my classroom, people would be logged in, and I could see who the first 2 people were who stuck with their answer. But it's whoever student B is, and then H. Somebody still hasn't changed their wrong answer. So yeah, friction is not going to be any bigger than the static friction isn't going to be any bigger than the force that it needs to be, and the force it needs to be is that component of gravity going down the incline.
I think you were looking at drawing incline because it's going this way.
Oh, thanks. Yeah, that's right. Yeah.
That's what it was to be able to get right cosine. I was like.
Yeah. We liked the D. Oh, it's just they were differently labeled. Yeah, one of these. That's normal. Okay.
Yeah.
But yeah, sorry about that. Good observation. That's why it's helpful to have the bigger picture in mind. All right. So how about so we did that tricky one.
We can use a trick again.
This one, you know how we saw a couple little errors on the free response? Well, this one is not quite drawn to scale, but they're
The following students should meet at the lobby table to receive their gift cards. Lily Hayden, Noah Jeffers, Alex Milligan, Maria Rushing, Ella Bozard, Bailey Furness, Joe Welch, Hayden Lilly, and Max Brown. We will now rotate to our next session.
I know. I'll go get your gift card for you. It's mine. Don't worry.
Yeah, you guys need to take a little stretch? Alright, we're gonna be much more smooth now here from here on. Although we might do this, we might do these a little bit more, because the next one's a lot of free response.
That thing is right on the.
So, if you need to give this to somebody, I'm about to.
Oh, you're taking off? So there's the, for your corner over there.
Oh, thank you.
He has to take off or something.
Okay.
We, we'll be using it for the last packet as well. But yes, we are going to,
Oh my goodness.
okay, yep, excellent. AP Biology, yep.
It was really fun time we had.
Yeah. So you're gonna stay in biology for the second half of the day?
Yes, sir.
Gotcha. Yeah, the gravity one's less.